Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 29, 2025, just yesterday. It introduces Ouro, a looped language model family that bakes reasoning into pre-training through iterative latent computation, showing that compact models with 1.4 billion and 2.6 billion parameters can match or beat state-of-the-art models up to 12 billion across many benchmarks. The paper is titled, Scaling Latent Reasoning via Looped Language Models. And as we'll see later, the implications for training efficiency and more faithful reasoning traces are quite significant. Figure 1 shows why looping matters for parameter efficiency. The left panel sketches the looped transformer with an exit gate, which is a learned module that decides when to stop the recurrent passes based on difficulty. The middle radar plot highlights that the Ouro 1.4 billion model competes with larger baselines across reasoning tasks. The right radar plot shows the Ouro 2.6 billion model matching or surpassing bigger systems while running with 4 recurrent steps. Alright, Figure 2 shows that looped models climb advanced reasoning benchmarks against strong baselines. The Ouro model with 1.4 billion parameters stays competitive across math and science tasks. The larger variant uses 2.6 billion parameters and improves further. On several datasets, it matches or exceeds models around the 8 billion tier, which signals strong parameter efficiency. Bars labeled pass at 10 denote accuracy when the system may try multiple solutions. Alright, Figure 3 presents the looped architecture and what it means for compute control. This figure shows 2 panels that contrast training and inference. On the left, shared layers run for several recurrent steps while an exit gate, a small classifier that predicts when to stop, learns under an entropy bonus to explore depths. On the right, the model exits when the cumulative distribution function, the running sum of exit probabilities, crosses a threshold so harder prompts get more steps. So, while Figure 3 covered compute control, Table 1 lists the core architecture choices for the 2 Ouro models. Both models share multi-head attention, a SWI-GLU feed-forward network, and rope positional embeddings, which rotate representations to mark token order. The smaller model uses 24 layers. Its hidden size is 2048. The larger model reaches 48 layers. Both use a vocabulary of 49,000 tokens. Table 1 covered the setup, and Table 8 compares the 2.6 billion looped model against larger dense baselines. The table means the recurrent design delivers stronger reasoning for its size, because it allocates extra compute only when needed. On MMLU Pro, the looped model reaches about 56. That surpasses an 8 billion baseline. On Math 500, it posts around 91. GSM, 8K, and BBH also come out ahead, while the model holds roughly 2.6 billion parameters. Wrapping up, 2 takeaways stand out. Looping latent computation during pre-training delivers strong parameter efficiency, with 1.4 and 2.6 billion models rivaling much larger systems, and adaptive exit gates let the model spend compute only when needed. The broader implication is a new scaling axis that favors controllable, more faithful reasoning. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.